Good morning. Let us resume our discussion. So what were we discussing in the last class? Can any of you give a couple of points? What is the topic that we were discussing in the last class?
We saw various slides on scale invariant feature transform, and we saw how matching is more prone to errors than the key point localization. Then we discussed about HOG and feature descriptor of the scale invariant feature transform. And then we ended our discussion with bag of visual words approach as a descriptor.
Yeah, very good. So we will discuss a little bit more on bag of visual words, as this is the well-known descriptor. In fact, this encompasses the shift descriptors within it. Okay, and it's a high-level descriptor we can consider in that way. And this is also widely used in many of the computer vision tasks, not only on classification, but also on some other tasks, classification, recognition, even object detection, and parts-based models, wherever we don't wish to take the whole thing into account, but still wish to have a consolidated view of the object. So in all these things, this gives a very good feature vector for us. So we will discuss a little more on this. While discussing this, we also need to understand and know a little more about the classification and the clustering methods. So let's review first on the classification and clustering methods, and just basic methods on classification and clustering. I will give one example for each, which were already discussed in some sense, but I will give a little more details on them, and then discuss on the bag of visual words. Okay, and then let us see a couple of slides on bag of visual words to understand them better. Okay, so overall in machine learning, so what kind of, say if I want to perform classification, okay, what is the task of classification that we do is, if we have several samples, okay, these are all, let these be samples. I am plotting against the features of the sample x1, x2. Assume that I have sample 1 and then up to sample 1000 or 100, whatever. Okay, 1000 samples. And for each of them, we have extracted some feature vector. It can be usually d-dimensional feature vector, but for understanding or ease of discussion, we are bringing it to a two-dimensional feature vector, d cross 1 or 2 cross 1. Okay. So the task of classification, clustering, all these things revolve around grouping these samples into different categories. Okay, so there are, as we discussed before, there are a lot number of applications which needs this. Say blood cell classification. Okay, in medical applications, blood diagnosing different blood count, for example, complete blood count if you wish to get. We need to see how many red blood cells are there, how many white blood cells are there, and so on. Okay, platelets are there. Okay, cancerous cells are there. What kind of cells are they? This similarly, there are several other applications even in medical imaging, medical applications. Say for example, chest X-rays, pneumonia. Is it infected by pneumonia or is it a normal chest X-ray? Is it infected by COVID? Okay, and so on. Even in pneumonia, there are several classes. 14 different classes you can see. So similarly, there are several others. Say cancer, if we have a mammogram image of the chest, is it cancerous? Is it infected by cancer? Is it malignant or benign? That is not normal, or is it infected by cancer? So like that, there are several applications where we need classification as a very important task. Similarly, in computer vision, as you can see, classifying the persons, objects, all the aspects are to be differentiated first to make a better sense out of it. Say if I want to identify what the scene is, first we try to identify what the objects are. And then we would like to classify each object as which object it is. Okay, and thus classification forms a very important role in terms of our inference of the real world. So that's in computer vision. Similarly, in satellite image processing, we would like to classify buildings, water, okay, and then road, many other things. Even if you would like to have self-driving cars like of applications which demand, which are based upon these basic applications, which are specific and based on these basic applications, they also demand. Say, if we have a if a car is moving, we would like to know who is what, which object is in front. Okay, and how is there an object in front is the first question. How far is it from the car that we are driving is the first question. After that, we also want to know where the road is. Okay, where is the road ending? Okay, and what are the objects in front? Okay, because the velocities will be quite different from car, person, and so on. So all such things make a important task. And for all of these things, the classification or the grouping is an essential thing. So what we see now in as we discussed is, first we understand about the basic classification methods. Okay, very basic classification, and then grouping or clustering. See, in some cases, what may happen is the classification is divided into supervised and unsupervised classification. In some cases, what may happen is we need to start with no information, no prior information. Okay, I am just given some samples. Say, assume that I am given your marks. Okay, and I want to cluster your marks into grades. Okay, A, B, C, D, and so on. How do I cluster or how do I group them? I don't want to take an a priori knowledge that this person will go to okay A and so on. Okay, so it's not a supervised classification problem. Supervised classification means we have enough data, okay, which is already pertaining to different classes or groups. I wish to categorize the test data. Okay, taking advantage of the training data, I classify the test data. Okay, that means if I have 1,000 samples, among this I know a priori that say out of this there are C1, C2, and C3, 3 classes. If these samples goes to, so 200 samples are from C1, and then there are maybe 300 samples in C2, and then remaining 500 are in C3. Okay, and now if I am given a test samples, okay, again 1 to S100, 100 test samples, I would like to put these 100 test samples into one of the categories. Is it C1, okay, or C2 or C3? That's the question we ask. That means we first give some training data wherein the class labels are known. Okay, and then I ask a question, is it C1 or C2, okay, or C3? Okay, this is the classification problem. This is training data, and this is test data. This is supervised classification problem. Okay, so there is another supervised classification problem wherein we start with, say, for example, if we are given test samples, S1 to directly S110 to S test data, S1 to S100, how do I put into 3 groups? I don't know which is class 1, class 2, class 3 also. After putting into 3 groups, I say that, okay, this is likely class 1, this is likely class 2, this is likely class 3. Okay, so that's 3. How do I arrange without having any prior information? That's clustering. This is referred to as clustering or unsupervised classification. Okay, so if say all your exams, if they are asked in the syllabus that we discuss, okay, that's a kind of supervised classification where you are expecting you are anyway giving good training, and then you are learning on the subject that we discuss, and then you will be answering on that. Okay, you are putting into your knowledge from there. Okay, unsupervised means you say if you go to an interview, okay, they may ask anywhere anything. Okay, so that you can consider in some sense as an unsupervised. Okay, testing. So in general, what we are given in either of them is we are given good number of samples. So you can consider that what is that I have plotted here with intus. Each is a sample. Sample means it can be, say, face. For a face, if I give features like where distance between eyes to nose, okay, these can be 2 features. So, or if I have a fish, I may measure length and width. Those are the features. If I have a digit, if I calculate the number of non-zero pixels, okay, and then the overall area it occupies or whatever, Okay, that's again a feature. Those are the features. So I can also calculate the length and width for even the digits. So all these are the features. So in a given problem, as we discussed at the beginning, okay, problem to problem, the features differ, and we have seen many methods now where to extract features and how to extract features. After extracting those many features, this feature one, okay, what essentially we have got finally is this feature one, first feature or whatever, and then feature two. Since we can't sketch easily more than two dimensions, we have sketched them in 2 dimensions. So like that, now what we have, these are all the different samples. This may be S10 or whatever. Now the question is, if I ask you a classification, supervised classification problem, let's start with the supervised classification. So what is the method so far, you know? Supervised classification. If you wish to perform, do you know any method for performing supervised classification? Given the samples, now given the samples are S1 to S1000. Okay, these are all, assume that these are all the training samples. Okay, now given these training samples, well, how do you classify the 100 test samples? That's the question. Okay, so now what is the method that you know? Can any of you tell quickly what the method, any of the methods that you know for supervised classification? How do you address this? A quick answer is welcome.
Something like template matching.
What's the template matching? Very good. So here template matching, if we give images, anyway template matching. Here what matching do we do? What is that has to be seen, whether they match or not? So what is the equivalent of template matching here?
Data matching.
Data lab is it.
Data matching.
Data matching. Okay, more specific, more clearly here. I am giving
Feature matching.
right?
Feature extraction.
Feature extraction is done. This is the feature vector. Okay, X. Okay, for the kth sample xk. Okay, and you have for all k equal to find 1 to 1000. 1000 samples are at our hand. Okay, training samples. Okay, and then test samples here. Here X test stamp, K test sample A, right? Okay, and then these are K equal to 1 to 100. 100 test samples we need to classify. So how do you approach? I need a mathematical framework, or we need a little bit more clear picture on how do I approach on this problem.
Distance measure.
Distance matching. So fine, distance matching on the feature vector we perform. So what we do is each of them has a feature vector. So we see, okay, X test sample, okay, a feature vector. Assume that we have only first one set test sample. We see what is the nearest neighbor. Okay, we among all training samples. Okay, so what we see is the distance between X test, comma xk. Fine. For all k is equal to 1 to 10,000. Okay, we calculate the distances. And then what do we do? So this is test sample and then training sample. We have calculated the distance. Matching here is better to be written as closeness. Okay. Of test sample to training samples. Is what we are measuring. Okay. And then what do we do? We take the distances. After taking distances, what do we do? XT belongs to that class CJ.
If the distance between the XT and
Distance is
XK
minimum.
of the class
Between, yeah, the
XT,
XT and the sample XK star, if I say, okay, is minimum. Okay, and then XK star belongs to Cj. Right? So if the distance between X test sample and the Xk star, K star is a sample with which the distance is minimum. So we collect the first distances and see for minimum distance. Fine or not? That's what we are looking at. Right? And then the xt belongs to that class to which the nearest neighbor belongs to. Is it not? So xk star is nothing but the nearest neighbor. Nearest neighbor of what? Nearest neighbor of what? Xk star is nearest neighbor of what?
Xt.
So why we are saying nearest neighbor? Any idea on this? Any idea why we are saying this is nearest neighbor?
The distance is minimum between xt and xk star.
What is that?
The distance between xt and xk star is minimum.
Right, very good. Distance between xt and xt star is less. Okay, it's not minimum, it is less. But still we say it is a nearest neighbor. Any idea on that? Why? Your answer is correct. I just want a little bit better visualization on that. Because see, from now on, when we go on to the, see, so far we have seen the images and then we are trying to relate with the templates and so on. Okay, so we get a feel of what is happening there. But when we move on to the features of the image, say finally we have got HOG vector, maybe of 128 cross 1 dimension, okay, or whatever dimension. Okay, and now we have only a feature vector, one-dimensional feature vector. And I want to get a feel of what is happening, okay, on the samples now. Like say we have each patch, if you consider as a image, or if you consider for each image you have feature vector, you have now 1000 images. Okay, so 1000 samples I am saying. I am describing those samples by some feature vector now. Okay, now I want to get a feel of what is this minimum distance or why we call it as nearest neighbor and so on. So why do we call this as nearest neighbor? This method of using this nearest neighbor is referred to as nearest neighbor classifier. What we have discussed now is nearest neighbor classification. So did anyone got a feel of what is this nearest neighbor? Or could anyone give us a better idea on what is, why do we call this as nearest neighbor? Yeah, you should tell now. You should be able to see all things are here, right?
Because the features of that neighbor closely resemble to our features of our test.
Features of?
Of all the samples present around XT, XK star is the closest neighbor. Like it's like the shortest distance.
Very good, very good. So you can consider that if I see XT somewhere, okay, if this is XT, yeah, for example, if this is the test sample XT, okay, then what we can see is among all the samples, okay, this sample is quite nearest to it. Okay, it's very closer to this. Okay, so in some sense, this is the S3 is the nearest neighbor for XT. Okay, if you see in terms of, even if you visualize in that dimension, okay, it is the neighbor of it. So if you plot XT, S1, S2, S3, also all samples, S3 is the nearest neighbor here, right? Features of S3 are quite close to features of XT. That is also fine. Okay, so here, as you can see here, features of X3 are, say, you can say that, so features of X3 are quite closer. So this is this implies S3 is nearest neighbor of XT. Okay, this indicates that, right? So hope you people understand this. This is the nearest neighbor classification. Okay. So on the top of this nearest neighbor classification, there are few other nearest neighbor classification methods. Those are referred to as NK nearest neighbor classification methods. See, instead of looking at, say, what may happen is, say, in, let me sketch somewhere differently. See, as we are discussing on the supervised classification, we know the labels. So these three, let these be belongs to one class. Okay, anyway, these samples belongs to one class. Let these samples belongs to another class. I am sketching with a different color. Okay, and these samples belongs to another class. Okay, now assume that we have a test sample. Okay, somewhere. Test sample is, say, assume that it is here. Okay, test sample is here. Okay, now, if I see the nearest neighbor for this test sample, again, what are these axes? X1, X2. So X1, X2 refers to features of the samples. So what are these intos? All intos corresponds to what? Samples. Which samples? All intos corresponds to which samples? Training samples. Okay, and then what is circle corresponds to?
Test sample.
Yeah. And circle corresponds to test sample. So if I give you this, you can know how many samples are there, how many classes are there, and so on. So color coding indicates which class they belongs to. C1, C2, C3. Okay, or are shown with different color. Okay, here, right. So now the question is test sample to which class the test sample has to be classified. Now X1, X2 are anyway features. Okay, and then nearest neighbor classifier. Now if I consider to which class test sample X0, say XT belongs to. To which class does it belong? Say if I name these as say assume that this is class 1 and this is class 2 and this is class 3. Okay, and then this is XT is test sample. Okay, so X by nearest neighbor classification. XT belongs to which class?
C1.
C1.
Huh?
C1.
Right. XT belongs to C1 because the closest sample is from C1, right? But actually what may happen, see if I, this is visually looking like this, fine. So I will make a small change to make to highlight the point that I would like to discuss now. Okay, so nearest neighbor is still the sample from C1. But as you can see now, if I see sample concentration, okay, around XT, which samples are more? C1 samples are more or C2 samples are more?
C2.
C2.
C2. So what do you think it's supposed to be classified to? Is it to C1 or C2?
C2 because the majority of the samples near the test belong to that class.
Right. So this can be a noisy sample as well. What may happen is, say, for example, while we are collecting the features, we may go wrong. Even the sample may be noisy. That means with while acquisition itself, there can be added noise. So for whatever may be the reason, taking decision just on a single sample may or may not be apt in all the situations. So this is decision is taken by decision of classification is taken by a single sample. Is it not in nearest neighbor classifier? Only one sample or single sample. Okay, and this can be noisy. So what is the better suggestion then? What should we do go then? We may take a decision based on more number of samples than single sample. In that case, the method in the method of nearest neighbor still can be used, but with 3 nearest neighbor. If we use 3 nearest neighbor classification, what do? Get the 3 nearest neighbors and give them majority voting, give them voting and classify based on the majority voting. Okay, then it belongs to which class? If I perform this 3 nearest neighbor classification, figuring out the 3 nearest neighbors and then giving the majority voting, then it belongs to which class?
C2.
C2. Then it looks better, right? So this 3 nearest neighbor, or in some cases 3 nearest neighbors alone may not be sufficient. Say if we have so many number of samples, what can happen? Close to this sample itself, there can be 5 samples or even 100 samples. In that case, taking just a call on 3 nearest neighbor may not be very apt. So we'd like to go for 7 nearest neighbors, 11 nearest neighbors, and so on. Usually we take with odd number of nearest neighbors, because majority voting will easily boil down to classifying into one of the class without having ties. So 3 nearest neighbor classification, what do we do now? We pick the find out the first 3 nearest. We find 3 nearest neighbors. And then the sample is classified to, test sample is classified to based on majority voting in these 3 nearest neighbors. Okay, so if we perform this, then what will happen? This enables us to classify XT to C2 rather than C1 as in 1 nearest neighbor. Okay, is this clear? This method is referred to as K nearest neighbor classification. Any questions on this?
So in this case, like we have 3 classes. If I use 3 nearest neighbors, suppose the labels come out to be like 1 from each class.
Right.
Then
what can we do?
Then should we increase number of
Nearest
neighbors?
neighbors, you can do that, or you can, if you would like to still go with 3 nearest neighbors, you can take the top one. So on the top of this majority voting, we can give the priority if there is a tie. That means in that case, there is a tie in the sense that all 3 have equal number of votes. So then we go for the nearest neighbor, like which is the smallest distance.
Okay.
Yeah, fine, good. So you can, in fact, what usually is a good exercise is if you have 1000 samples like this and then 100 test samples, if you make a sketch of 1 nearest neighbor, okay, and then find out the accuracy of all 100 test samples. So if I want to test all 100 test samples, what I do? I take first test sample and see which is the nearest neighbor and assign its class label. Okay, and similarly, then I see the second test sample, I assign its class label, and so on. I keep doing that till I complete all the test samples. Okay, while performing this, for each test sample, I need to redo the whole thing. Okay, so that I think you know even before. So the nearest neighbor classifier is not learning too much. Okay, it is essentially finding distances and assigning the label of the nearest sample. Okay, and finding distances need to be done every time as I get the new test samples. Of course, there are some mechanisms by which they divide the whole space of samples into different classes. That means a priori itself, I know that actually these are the samples. I say that this is the nearest neighbor boundary, in the sense that I say that this is referred to as tessellation of space. What do they do is, at the beginning itself, they divide the space into the nearest neighbor regions. Okay, so in that case, what happens? This whole region, whatever you get, so say if it is like this whole region is the class 1, this whole region, whatever test sample I get is in class 2, and in this whole region it is C3, class 2. Okay, like that. Of course, I can also divide this if I follow the first nearest neighbor approach. But if I go for 3 nearest neighbors, it is not that easy to do a priori. So we need to compute the distances, we need to sort them, and then we need to also give the voting and then decide on the class level. Hope this is clear. Okay, if we go for 3 nearest neighbors, then essentially what will happen? These are the 3 nearest neighbors. Okay, and then based on that, we take a decision for this test sample. Right? So what we can do is, as an exercise, if we wish to do. So for first nearest neighbor, what is the accuracy, overall accuracy on the 100 samples? Out of 100 samples, how many samples are correctly classified? If we know the labels for test samples as well, we can test that. So if in one nearest neighbor, the accuracy is, say, for example, this is the with respect to the accuracy, if we make a sketch, okay, or if we make a accuracy versus the nearest neighbor plot, okay, so this is the percentage of accuracy in classifying the samples. Test sample means all test samples. Okay, so if we do that, what will happen? So from first nearest neighbor, say assume that 80% accuracy I have got. 3 nearest neighbor, when I do, the accuracy may be, say for example, 86%, 84% otherwise. Okay, 5 nearest neighbor. What do you think will happen? If I keep increasing the number of nearest neighbors, what do you think will happen to the accuracy? What's your guess?
Up to some point, and then it will become constant.
Right. So it increases up to some point. Okay, and then it becomes constant, or will it decrease? Okay, it can also decrease as well. Because what will happen? See, if I keep increasing the number of samples, see, the first 2, 3, say here in this scenario, it is very easy to see that it comes to the class C2. Okay, and then settles. There are some examples wherein the samples need not be linearly separable, in the sense that here class samples of class 1, class 2, class 3, you can separate by a decision boundary, and hence they are referred to as by a linear line, and hence they are referred to as linearly separable samples. If there are scenarios wherein, okay, you can see here at the bottom where I am sketching a scenario. So if you see samples like this, okay, then they are not linearly separable. So there can be a large number of examples. In fact, in many of the real classification problems, you can't separate the samples. Okay, they are not linearly separable. Okay, so these are different color. Okay, so you can't separate, and then in that case, what will happen? It keep oscillating also, and then it can also decrease the accuracy if you keep increasing the K value. So usually the trend is it will increase up to some percentage. So it can go up to say 86% or whatever, assume that. Okay, and then it will keep slightly slowly decreasing or becoming a constant after some time. Okay, oscillating, decreasing. It can follow different pattern. Okay, it is not necessarily that it has to strictly follow this trend. Okay, but however, usually it is advisable, or it is better up to some extent having more number of neighbors to consider for classification. Fine. Any questions on this? Okay. So now let us come to the discussion on the clustering methods. So assume that I have some samples again. Since this is a clustering problem, I don't know a priori which class do they belongs to. I just know the samples. I was given some 1,000 samples again. In this case, I am able to easily visualize the samples because the dimensions I have considered are only two, or two features I have considered. Usually samples will have hundreds of dimensions, as you have seen. So, and then we can't visualize which sample is closer, which sample is closer to what other sample, where does it lie in the 100 dimension space, 1000 dimension space, and so on. Nothing we can visualize. So in such case, what we know is just some numbers or a vectors, okay, set of vectors. Of course, we can calculate the distances and then try to give some closeness measure and so on. Okay, but how do we separate these, or how do we group them into three different categories, three or any number of different categories? Okay, so any idea on this? So the question is, we are just given some samples, again S12, okay, S1000. Okay, you need to group into three classes. Assume that you are asked to group three, okay, three groups. So we are saying classes fine, because after grouping we can get the classes, but we are essentially grouping into three groups. Okay, and we straight away started with the test data. That means just to have the same notation or same numbers, we assume that we are given 100 test samples directly and asked to put into three classes. Okay, how do we approach? Any idea on this? So how do we approach is, see, you can see the distance. Say if you take arbitrarily, you start with three different samples, okay, being in three different groups. So I put randomly, okay, these three different samples to three different groups. I start with, say, X1, first sample, one sample, X15, okay, and then X50. I just started with the initial samples per group, for each group. Then what we can do is, we can see to this X1, which are all the samples that are closer, and then put into the group 1. Okay, I can formulate I can make the clustering. Clustering means grouping. Perform clustering. With these initial representatives. How do we perform grouping or clustering? Any idea on that? I want to put all 100 samples into these three groups, taking these initial representatives. How should I? Yeah.
Distance of these samples with X1, X15, and
Right.
X4.
So I calculate the distance of these samples. Any say I write for sample anyway, XK also I can write. Okay, for representatives, I will write mean. Okay, mean of these groups I consider, just to start with. So mean 1, mean 2, and then mean 3. Okay, I just started with this. So mean of that Cth class I have taken. Okay, for all C, 1, 2, 3. Okay, I find out the distance of K for all K equal to 1 to 100. All of them I have found the distances, and then Xk is put onto the belongs to Cj, okay, for which if distance between Xk and mean of Cj is minimum or is less than or equal to distance of Xk with m other Cs. So since I have written C itself as the variable, okay, Xk belongs to Cth class. If in case if Xk between distance between Xk and MC is lesser than MP, whatever, okay, where P is equal to 1, 2, 3 here. Okay, C is our MC star, let us write, considering our notation. Belongs to C star. You people are able to understand, right, what I'm writing here? Right. So among the C classes, where C is equal to again 1, 2, 3, C star is a class to which we are assigning. Okay, if MC star is lesser than or equal to M distance between XK and MC star is lesser than or equal to distance between XK and any other class MC. Okay, so this is referred to a what kind of clustering? We are performing anyway nearest neighbor based clustering here in this method. Okay, we are looking at the distance. Distance means I am writing distance here, but I hope you people know how to expand and write this distance also. D of xk comma mc, when I write, what does it mean? Norm of xk minus mc whole square. Hope you people know that. Okay. So now it's not, you frequently you may not see, but in computer vision community and even machine learning community, mathematics is a very strong base. It will come very frequently in all papers, books, and so on. So unless you understand some kind of mathematical notation, okay, and interpret from that, it's understanding any method was almost impossible. Okay, nowadays also it is needed, but it's relatively little lesser. But still you should have the skill of understanding what mathematical notations we use generally, and how do we write and how to interpret from that and so on. Okay. So this is the distance we take and this is the assignment we do. This is the kind of assignments. Oh, 2 different clusters. Then see, but we have randomly assumed some initial means, okay, for 3 clusters, but this may not be very correct. Okay, in terms of really separating them, the samples into different clusters. So what we can do now? Any idea on that? So what can we do to improve the clusters now? So these clusters, if I perform this, what may happen? Say with this, if I see mostly all these things may come into this. Okay. And then these assume that come to this. Okay. And then these all assume that it comes to this. Assume that like that. Okay. So, but this grouping is not correct. So what should I do now? Any idea on this? This is assignment. Samples to different clusters. Okay, that's what we have done here. So now this may not be very correct. So then what do we do?
Take the new mean of the clusters.
Yeah.
Yes,
So yeah. So what we can do is, usually in computer vision, the in fact in optimization itself, what we do is we may not wish to get the solution at one stage. Okay, we would like to go iteratively. So initially, say the plan is, if the means are correct, or that means if the representative for clusters are good, then if we use distance metric, I should be able to cluster them better. That's the idea. With that I start. But the representatives itself are not correct. But I have got the clusters now. So what I do now? Find better representatives now. Okay. Once I find better representatives, then these representatives will not have the previous clusters. Now find the new clusters again. Once I get the new clusters, again form the new representatives, better representatives for these clusters. Okay, for the new representatives now, form better clusters. This method is referred to as k-means clustering. It's widely known and well used. K-means and sometimes also C-means. Okay, k-means clustering. So this is a simple method. This has roots from many directions. Okay, it has roots from very well-known statistical method called expectation maximization. Okay, it also has very good importance in segmentation methods in image processing and computer vision. Okay, and so on. I will discuss some of the examples of this k-means clustering in image segmentation in subsequent classes. Okay, so now what these say assigning samples to different clusters are cluster representatives. Okay, so now, but these are not very good. So what we do? Form new cluster representatives. We start with initial samples. Okay, initial samples are initial representatives. I will write here. Okay, and now form better representatives. What is the method to form better representatives? Any idea? I need better representatives, fine. But how do I get? No, MC, I want to get better. No, so MC, if I consider previous iteration, it is MC not or whatever. MC in the next iteration is equal to what? Summation xk. Xk belongs to Cth cluster. Cluster C. Okay. So like that, what I will do? 1 by NC. Okay, number of samples of that cluster. Okay, if I perform this operation, mean is the good representatives for the cluster, right? So new representative I will get. So new representative may be somewhere here. Okay, for this class, this may be here, this may be here, this may be here. Okay, now if I make another grouping, what will happen? Next grouping if I do. So these are the new representatives. Okay, I will make the new groups. So this may be one group now. Okay, and this may be another group now. So this also here it may divide a little bit. Okay, so still this may be another group now. And then this may be another group now. Like that. Okay, so this also may not be very good. We may go for another iteration. Okay, so like that, what we do again for better representatives, form better representatives, and then again what we do, the next step is again cluster. Assign samples to these representatives. Okay, and then again what we do? Again form new representative, better representatives. Okay, and then again assign samples to these representatives. And then iterate till when? Till converges. How do we define convergence here? Any idea?
The next MCs will be same as the previous.
Yeah, when previous MC doesn't change. Or assignment does not change. Okay, so if we consider MC in Tth iteration minus MC in T minus 1 iteration, okay, is equal to close to 0 for all C. Okay, so this is the convergence. This is referred to as K-means clustering. I will show probably some of the pictorial depictions of this probably in the subsequent classes. Okay, but this is widely used clustering. So you should know how to group samples. Okay, and you should know how to classify samples with the basic methods. Even for the discussion of many of the computer vision methods. Okay, so far we have focused on extracting features. Using these features, if you would like to perform a computer vision task, this classification or clustering is essential. Okay, so now before we conclude the class, let's get a picture of bag of visual words. Since we discussed in the last class, okay, now let's get a better picture of bag of visual words. With the background of knowing the clustering and so on. So the problem there is, so we have actually several training samples there also. Training samples means training sample images now. Okay, corresponding to, again, assume that 3 classes only. Okay. for which say we started with this. This is the input data. Okay, and then the test data or the output, expected output is our task. Given a test data of S1 to S100, classify them to 3 classes using bag of visual words. This is the problem. Assume that this is the task we were given. Now, what do you think is the next step, first step for performing this? What is the first step? Given the images, S1 to S100, S10,000 in fact, what should we do with this? What do you think is the first step in bag of visual words based on the discussion that we had in the last class? None of you remember? Okay, so what we wish to do is we anyway know about the key points where the information to be looked in all these images. And then around each key point also we know what information to be looked at. So get the feature vectors, that is scale invariant feature transform, feature vectors for all key points in all images. Okay, so if we can extract this can be the first thing, because we know how to extract the features, how to key points, how to extract the features. I will just tell the steps and then probably we'll go ahead in the next class. You people have a next class now? Are you people free for some time?
We have a class, so.
You have class. Okay, fine, good. So then I think we will conclude and resume in the next class. So the next step is we want to use supervised setting here. Okay, so we would like to put all these features into the known categories. If you know that this class 1, class 2, class 3 samples, okay, we want to get the feature vectors for only class 1, okay, class 2 and class 3. And we want to get the bag of words, first of all, okay, for these class 1, class 2, class 3. And then we form the bag of visual words descriptor. Okay, so we'll see that in the next class in more detail. So before I close the class, if you have any quick questions on the classification and clustering, okay, or on the bag of visual words, you can ask. Fine. So let's discuss this in more detail in the next class. And then subsequently move on to the discussion on the segmentation methods and then the depth extraction methods. Okay, to conclude the discussion on the computer vision tasks. Thank you then.